Thank you very much. Good morning. Well, I'm presenting this work. It's complete biogas desulfurization and calorific value enhancement in compact absorption units coupled to microalgae bacteria systems. The title is very long, but the work is quite simple. First, I would like to introduce our research group. We are located in Querétaro. Many of you, I know that you know the city and the lab, so those who are not familiar with the group, you are most welcome in Querétaro, whenever you want, not only in November. Well, the team. We have talked a lot about the biogas and the renewable energy. I will not spend much time in this. We can produce biogas from a wide range of organic residues. Okay, and then we have biogas, which is mainly composed of methane and CO2. So one of the key applications of biogas is to use it directly, burn it in engines and combine heat and power systems, such as this one. And we can generate electrical and thermal power. But biogas, raw biogas is never ready to use. We also have to apply some technologies to purify it. Sometimes we have to enrich it. But usually purification is mandatory. In this case, for H2S, H2S can be in very different concentrations. You can find 1,000, 5,000. We have measured even 20,000 ppm of H2S, which is a huge 2% of the biogas. So it will destroy your equipment in a few weeks if you burn biogas in this way. Okay, so we have to treat, to perform a desulfurization of this biogas. So the problem is very simple, it's corrosion. You can destroy the engine, but also the pipes, if they are of metal pipes. So this is the problem. There are a lot of biological technologies to desulfurization technologies. You can use bacteria, aerobic, anoxic, but this is a very interesting one because we can combine wastewater treatment performed by microalgae and bacteria, and you can hang up the desulfurization system. Okay, so it's very simple, the process. You have, bacteria consuming organic matter, producing CO2, which is used by microalgae to produce oxygen, and the cycle goes on. So it's very cheap, this treatment, because it's driven by sunlight. So it's a very good alternative for wastewater treatment, low cost. And you only hang up, okay? So you put your absorption unit so you can enter this system very quickly. And the H2S can be converted into sulfate or elemental sulfur, depending on what you want. Elemental sulfur can be really valorized as well. So this is the typical configuration of a biogas purification and upgrading system. This is a conventional high-rate algal pond. Many of you know these systems. And then you are recirculating the liquid media, and you perform here the biogas purification. So the idea is to absorb CO2 and H2S, so you have enriched this stream, and we call biomethane, okay? So the key objective of this technology is to produce biomethane. If you make a literature review, you will see that this is the key objective of this technology. And the key operating parameter for biogas purification and upgrading is the biogas retention time, or gas retention time in general. So it is a very simple relationship. It's comparable to hydraulic retention time, but in this case, for the biogas. And the most typical GRT value that you can find in the literature is around 60 minutes, 1 hour. Okay. But if you make a calculation of what kind of absorption unit, bubble column, for instance, you will have with this GRT, is huge. It's like a 20-floor building. So it is impossible to implement this in real life, So we have to do something. Sometimes we only stay in this step and we don't think about what is the equipment that I will need to perform this process. So the goals of this work are two, very simple, to determine the H2S removal capacity of a compact absorption unit operated at shorter gas retention times, and determine if calorific value enhancement can be achieved under such short gas retention times But I'm underlined under a realistic biogas composition because this is another problem. If you review the papers published on this matter, you will see always that the synthetic biogas mixture used in the experiments is composed of methane 70%, which is not very realistic. If you measure in real life, the biogas, in the best cases, is 60%, no? 50, 60%. So starting these experiments with 70% is a huge, is not very realistic. So this is the proposed configuration. You see it's much smaller. We tested two configurations, air-lift systems and bubble column, which is the typical one, and exactly the same. Okay? Why we are proposing this? Because in many cases you don't need to perform the complete CO2 removal. You only want to clean the biogas so you can burn it and use it in situ to generate energy. Okay? So if you use biogas retention times in the absorption module of 30 minutes, you will have still a very high absorption unit, 32 meters. But if you use 10 minutes, you will have something that can be applied. So let's see what happened with this. So this is the experimental setup. As I will not go deep in the description, but the most important thing for us was to try a synthetic biogas mixture more realistic. 60% in methane can be found. Okay, the H2S concentration was 5,000 ppm, which is also a high concentration in H2S. Okay, and we tested this relationship. LG is the liquid recycling rate, is related to the biogas flow rate in the column. Okay, so and very conventional operating conditions for the wastewater treatment. Results, we have a first startup period of 30 days. The first days we operated as a batch to promote the growth of the microalgae community. And then we started the operation in continuous. Actually, both biogas and liquid phase were operated in continuous mode. Okay? After this startup period, we started to decreasing the biogas retention time to 30 minutes, 30 in the air-lift configuration. Okay? Here, this line is the initial concentration of the biogas for methane, and this is the initial concentration for CO2. And we observed that we increase the methane concentration and we decrease somehow the CO2 concentration. Okay? So the most important for us was this. The H2S was completely depleted regardless of the gas retention time you use, because it's quite soluble and easy to remove H2S. But we were interested in observe if at 10 minutes we obtain some good results on CO2 removal. That means that you increase the calorific value of the biogas. Okay? So we have some interesting results in such a short gas retention time, and we can observe that. Then we also monitored the dissolved oxygen concentration. It was a sensor, online sensor, and we can see here that even under this short gas retention time, you can think it about loading rates of H2S and CO2 in the system. So when you increase a lot the H2S, you will have more requirement for oxygen, for oxidizing the H2S absorbed. So we were very happy because it was not depleted. So you can combine the treatment of, a very large flows of biogas, and you don't deplete the oxygen concentration, so you can treat as well the wastewater. It's not compromised. The same observation goes for the pH, because in these cases you are having a high load of CO2 and H2S, which are both acidic gases. So the pH will decrease, and we observed in all cases the pH was about 7. So very good news. No acidification. The main conclusions: the complete H2S removal can be achieved with compact absorption units as short as 10 minutes. So they're very, very small. The biogas calorific value enhancement you can achieve with the bubble column 5% or less, and with the air-lift configuration almost 15% of the calorific value which is very, very considerable. So it was very interesting. If you're interested in this subject, you can check this paper. It was published the last year, I think, yes. And thank you very much for your attention.